next presentation is actually from a company that's very dear to Kaust, and actually that we respect a lot, because Glosten is a company out of Seattle, Washington, in the United States, and they're helping us build our new Kaust research vessel, which will be environmentally friendly, low carbon. And this company, Glosten, is a leader in naval architecture and developing innovative solutions. So we have two speakers from Glosten who have been kind enough to present some of their work today, some of their innovative work. So we have Sean and Robin, Sean Caughlan and Robin Madsen. Sean is a senior marine engineer at Glosten, which is a full-service marine consultancy company. And he's a professionally licensed mechanical engineer in Washington and one of the industry's leading experts in the design of alternative fueled vessels, battery hybrid vessels, and electric vessels, including electric ferries, roll-on, roll-off ships, and research vessels. And he's currently leading the design of a floating hydrogen refueling station in California, which manages the conversion of Washington State's ferry passenger vessels from diesel electric to hydrogen. And then Robin Madsen is a senior marine engineer also at Glosten, and he offers experience in all aspects of the vessel systems engineering and for various types of vessels. And I'm sure we'll hear some very interesting discussion from them about how to actually make these hydrogen ships for marine applications viable technology. So we can see you guys, Sean and Robin. And yeah, the screen is showing now. How about the sound?
Can you hear me now?
Yes, it's good.
Right. Can you hear me okay?
Yeah, we hear you.
Great.
All right. Thank you very much. It was a very interesting presentation that preceded us. And thanks for the introduction. So my name is Sean Caughlan, and I'm going to be presenting on practical considerations of hydrogen as a marine fuel, and also with my colleague Robin Madsen. So thanks to Kaust for inviting us to this conference, the Hydrogen-Based Mobility and Power Conference, and I will proceed. So let's see, there we go. All right, so just brief introduction to Glosten. Is my slides advancing? Did the slides advance? I can't tell. All right. So Glosten is a full-service marine engineering and naval architecture firm. And we're involved in both ship design. One of our specialties is research vessels. We have groups in ship design, marine engineering, ocean engineering and analysis, as well as we're involved in a lot of marine civil construction. Noise control engineering is a specialty of ours, especially with research vessels, and of course, electrical engineering and shipyard production engineering. So just an example of some of the projects that we are working on. So we, of course, do ferry design. We do research vessels. We do a lot of workboats, such as tugboats, and we also are active in floating wind platform design through our Pelestar system. And then we've done some really we're well known for doing sort of interesting one-off challenging solutions like floating X-band radars and so on. And as was mentioned, one of our projects right now is designing the replacement for the RV Thule for Kaust. So I'm going to talk just briefly about some of the hydrogen projects that we've been involved with recently. So starting in 2017, Glosten partnered with Sandia National Laboratories and Scripps Institution of Oceanography with funding from the United States Maritime Administration. And we were challenged with, can we design a hydrogen-fueled research vessel with a 2,500 nautical mile range. So this became the concept for the Zero V, we called it, which is a 52-meter research vessel, and part of the challenge of storing that hydrogen resulted in a trimaran hull, which was a little unconventional. But to get the range, we had about 11,000 kilograms of liquid hydrogen on board. You can see the large liquid hydrogen storage tanks on the aft deck, and we were powering the vessel with about 1.8 megawatts of fuel cells. So this concept went through class review at the concept level, and also from the science group at Scripps, and that ended up being a larger vessel than they were looking for. So we sort of had a follow-on study, which resulted in a smaller vessel, which was more in the budget of what the university was looking for. And this vessel was, the idea here was to use as much hydrogen as we possibly could, and that would allow them to get their shorter range, so it turns out that about 75% of the missions that the university does are sort of 1 day or less. They take students out and on sort of 1-day missions and that sort of thing. And we found that we were able to do 75% of the missions with hydrogen alone in a much smaller package. And then for the times when the university did require the vessel to go out for longer missions, we have diesel available for that. So you can see here it's a 38-meter research vessel. It's about 330 nautical miles of zero emissions range and 3,200 nautical miles of overall range, which will serve their needs. And we did this with about 730 kilograms of usable liquid hydrogen in the tank there on the aft deck, and about 800 kilowatts of fuel cells. So this feasibility project led to our next project, which is actually underway right now. This is going to be a real vessel. This is funded by the state of California, and this will be Scripps Institution of Oceanography's new research vessel. So this is the Coastal Class Research Vessel, or the CCRV. Currently, this is slightly larger than the concept at 40 meters, but similar in terms of performance. Another project that Glosten is actively working on right now, as was mentioned, is a hydrogen fueling station. So this is a project that's funded by the United States Department of Energy, and our partner Hornblower Energy, along with the partners you see across the bottom: Air Liquide, Sandia National Laboratories. Nel is providing the electrolyzers. IGX is providing the storage tanks. So this is a demonstration project that will be built in San Francisco Bay. So there's several hydrogen fueled vessels that one of them's built and going through trials right now, and will soon be operating in San Francisco Bay. The one shown here, the vessel exists, but is being converted to hydrogen fuel. So these vessels are going to need a place to fuel, and the preference is for them to be able to operate on green hydrogen. So it turns out that San Francisco's power comes from Hetch Hetchy Dam, so they get most of their power from hydroelectric. So the idea was, can we produce green hydrogen at the point of use, which of course reduces the need for transportation. And hopefully reduces the cost. This is still considered a demonstration project, and the goal is really to see if we can demonstrate a floating hydrogen station rather than can we really produce it economically at scale. But this hopefully is the start of something. So this platform will produce about 500 kilograms of hydrogen per day using a Nel electrolyzer, 1.2 megawatt electrolyzer, and it will, like I said, it will be able to bunker the vessels right on the water, right near where they're being used. but it also has the ability to supply hydrogen to tube trailers for use on shore. And also because these vessels often have batteries, it will be able to provide vessel battery charging. Here's just a brief overview of what this looks like. So this is a it's not super big, as I mentioned. It's kind of a demonstration scale. But you can see on the left is our sort of control station. In the middle, we've got our electrolyzer and power supply. We're taking power from shore from a 12 kilovolt power stanchion. In the middle, we've got a reserve space for a demonstration fuel cell, which was part of the proposal, and the Department of Energy may want us to do that. So then the hydrogen which is produced is sent over to a compressor through a buffer tank, and then is compressed at 500 bar in the storage tanks over on the right side of the image. Now to get it onto the vessel, we have a hydrogen bunkering station, which also has the ability to cool the hydrogen to improve the transfer rate to the vessels. So we have two sort of loading arms, we have a loading arm for going ashore, and we have a loading arm for going onto the vessel, as well as a charging stanchion. So I'm going to hand the presentation over to my colleague, Robin, to talk about hydrogen.
Thanks, Sean. So presently, hydrogen as a marine fuel is typically stored either as liquid or as compressed hydrogen, though there's a lot of interest in and research in other storage, such as liquid organic hydrogen carriers or metal hydrides. Principally today, liquid and compressed hydrogen are the two viable paths. Liquid hydrogen, of course, is cryogenic at negative 253 degrees centigrade. And because of that, it's always boiling. And that requires pressure management of the boil off in the tanks, and also presents a challenge that the tanks have a limited hold time, in that as the pressure builds from boiling, you either need to consume it with the vessel or reliquefy it with a reliquefaction plant. And as a propulsion fuel, reliquefaction is not really a viable path on most vessels. Liquid hydrogen has a much higher volumetric energy density than compressed hydrogen. And so that makes it more appropriate for large quantities in larger vessels. And typically the liquid hydrogen tanks are on open deck, which presents an arrangement challenge. They can be below deck, but typically, when possible, they get put on the open deck, as we've also seen typical with LNG tanks for liquefied natural gas fueled vessels historically, which is kind of the model that liquefied hydrogen follows. For compressed hydrogen, it's stored at high pressure. 250 bar is currently what most marine applications are using, though higher pressure is certainly on the horizon. Because it's not cryogenic, it's stored at ambient conditions, it's not boiling, and so it can hold pressure indefinitely. So there's a big advantage of compressed hydrogen in that you can shut the tank down and the vessel can be idle without having to do pressure management of the tanks. One of the challenges, however, is that you need many smaller storage tanks, and so you have many connections to the hydrogen tanks, which presents many potential leak points and large hazardous zones. And we'll talk about hazardous zones some more in a little bit. It's got a lower volumetric energy density, and so it requires more space. And higher pressure tanks are still developmental. They're finding their way into land-based applications, but presently, 500 bar, 700 bar tanks are in development for marine applications and are not really employed today. Like the liquid hydrogen, compressed hydrogen is typically located on open deck, though there certainly have been projects where it is being put below deck, but there presents challenges of storing the hydrogen in an enclosed space. And compressed hydrogen is typically more suitable for smaller quantities in smaller vessels. Next slide, Sean. So when looking at hydrogen as a marine fuel, one of the largest challenges is fitting the fuel onto the vessel. Because it's stored in pressure vessels and independent tanks, it can't be stored inside the ship's integrated hull tanks. And so because of this, we must consider the tank system and the fuel together and not just the fuel itself. The tank systems, because they're pressure vessels, are an order of magnitude more weight than the hydrogen they contain. So if you look at this chart here, which shows the volumetric energy density on the vertical axis and the gravimetric energy density on the horizontal axis, this is considering the fuel and the tank system together. So hydrogen alone at 33 kilowatt hours per kilogram would be way out to the right. But by the time you add the tank system, which is about 10 times the weight of the fuel, it moves it pretty far to the left. So you can see in the top right of the graph, marine gas oil and heavy fuel oil, right? That's the current technology on ships. And we're trying to employ hydrogen that's down here in the bottom left. So the arrangement of fitting all the fuel required is a big challenge. This slide is showing a comparison of, on the right, a diesel fuel tank, in the middle, a liquid hydrogen tank, and on the left, a compressed hydrogen tank. They all have 153,000 megajoules of stored energy. And so that's about 1,275 kilograms of hydrogen or 3,500 kilograms of diesel fuel. And you can see the difference in size here is substantial, and this drives the challenge. And while the diesel fuel could be stored in the hull of the vessel, the hydrogen tanks need to be stored in these independent cylindrical pressure vessels. And the cylindrical shape of the hydrogen storage further produces challenges because the space claim of a cylinder in a ship takes up the space around it that's really not usable. So you can see in the case, you can see we put these rectangular bounding boxes around the tank systems. And you can see that the space actually required for the tanks are quite large. And for the compressed tanks, because you can't get tight packing of the tanks, you have all this lost space between the tanks. And for liquid hydrogen tanks, this is increased further by the tank connection space that contains all of the liquid connections and vaporizers and valves connecting to the tank. And for a relatively small tank, such as shown here, that can be a large portion of the space used. Fueling with hydrogen on marine vessels presents another challenge. Liquid hydrogen fueling takes its cues from LNG, which has already been well developed. And there are high rates of fuel transfer can be done with liquid, but it requires special procedures because it's cryogenic. But there's been a lot of learning in the industry around this from LNG applications that will transfer, though hydrogen, of course, is unique. One of the unique things is that purging with nitrogen is not possible because it will freeze. So helium can be used for purging and inerting bunker lines, so there's still some question as to whether they can be left with hydrogen in them or whether they will need to be purged. And I think that's something that's still to be developed. It's been done both ways on shore side and currently in marine, following the practices of LNG, purging and inerting is the starting point, but perhaps it won't be necessary. Fueling with compressed hydrogen, the challenge of this is high rates of fueling is difficult because you need large compressors and the rate of the heat of compression causes challenges in the storage tanks. So you can see the fueling process here where bulk liquid hydrogen is stored, vaporized, compressed, and then stored in pressure vessels, and then possibly boosted to high pressure, chilled, and then finally it is dispensed to the vessel. And for large quantities of hydrogen fueling, we expect that liquid fueling stations such as this will be necessary to store the required amount of hydrogen at the facility. Powering with hydrogen, I think there's been quite a bit of discussion at this conference, and I think will be more discussion on hydrogen combustion engines. They're very similar to diesel engines, and presently either in a dual fuel configuration where they use both hydrogen and diesel fuel as a pilot fuel to ignite the fuel in the cylinders, or as spark ignited engines that can operate on hydrogen alone. One major advantage of combustion engines is they can use a lower purity hydrogen. And they have low onboard emissions, but not zero, especially in the case of the dual fuel engines, because the pilot fuel does produce some emissions. So there'll be after treatment necessary to remove some of the criteria emissions that are caused from the combustion of the diesel pilot fuel. But a big advantage of combustion engines is they can be used for direct mechanical propulsion power, or they can also be used in a generator set to produce shipboard electrical power. The engine shown here is one of the B Hydro engines from ABC Corporation, which is the base of the engine for the Hydrotug. The other major technology for powering in ships is PEMS fuel cells. It's a very efficient electrical chemical process that has zero onboard emissions. And they're also near silent in operation, which can be a big advantage because noise on the ships is a significant concern. It's a concern in crew fatigue. It's a concern in passenger comfort. So having quiet machinery does have a value. These produce DC power, which needs to be either converted through a DC-DC converter to a DC grid or converted to AC for onboard ship use. And most vessels run AC power systems. And fuel cells require a very high purity hydrogen, which will be expected to be more expensive and more challenging to source, but is certainly available in the marketplace, and we expect to be widely available as fuel cell technologies become increasingly employed in marine and other mobility fuels. Next slide, John. So I mentioned hazardous zones a little bit earlier. This is one of the biggest challenges with hydrogen as a fuel on vessels, and especially for small vessels such as the research vessels that Sean mentioned earlier. You can see here the green spheres are all areas where there are potential sources of release of hydrogen, either in operation as a normal condition or an abnormal condition. This is areas around things such as the bunker manifold and connections to tanks, vents from fuel cell spaces, things of that nature. The large red area at the top is the hydrogen mast, which has a 10-meter radius area around it where it has to be kept away from ventilation openings into the ship, and away from the working areas of the vessel. So you can see arranging these areas on a small vessel particularly is extremely challenging. It takes a lot of thoughtful design of where to place the equipment and where to place your openings to try to consolidate this. And you can see here in these research vessels, it's very important that there be no hazardous areas in the working portion of the vessel, which is the aft deck, because one can't expect the people using the vessel, the scientists using the vessel, to have explosion proof or gas safe equipment on the vessel. So it becomes a major driver of the vessel's design. The principal rules applied to really all ships, but for hydrogen vessels, there's the flag administration, which is the state in which the country in which the vessel is registered. The marine classification societies, which are third parties that produce rule sets, and they do inspection and review of vessels to ensure that they are designed to a minimum standard and a safe standard. And it's generally a requirement of insurance for the owners to have a classed vessel. And then internationally, the International Maritime Organization, the IMO, develops rule sets that get broadly adopted through all of the flag states. And the code for ships using low flash point and gaseous fuels, the IGF code, is the principal code for that. However, presently, it doesn't cover hydrogen specifically, but more broadly, it was written for liquefied natural gas, really, and has very prescriptive rules for that. But hydrogen is still treated somewhat separately. So the definition for the regulatory definition for hydrogen is increasing, but it's still quite limited. And so the acceptance of a design must follow what we call the alternative design approach, where you must demonstrate an equivalent level of safety and reliability as a conventional oil fuel. And that's a substantial threshold to achieve with a low flash point gaseous fuel. So to achieve this, you must use a risk-based design and analysis that can demonstrate to the marine classification societies and the flag states that you've achieved this equivalency of safety and reliability. And this requires very close coordination of the design efforts and the construction efforts between the owner and designer and the regulators, either flag state or the Marine Classification Society. And I won't go through this chart on the right entirely, but what it's showing is this path through the design process from concept to preliminary design and then into contract and construction, where there's this iterative cycle of the designers developing the vessel design, the regulators are reviewing and approving design, and there's a substantial work scope in the center where you're collaborating to ensure that you are designing it to the correct standards, you have the correct criteria for acceptance of demonstrating safety. And it's a very iterative, cooperative process that requires a very close and frequent working relationship between the designers, the owners, and the regulators. And this model was followed for liquefied natural gas, and it kind of flows into hydrogen, but there's a lot of unique challenges to hydrogen. So we've provided a very quick overview of the considerations and challenges of hydrogen as a marine fuel. The technologies and the regulations are rapidly changing, and it's an exciting time in the industry, and it's exciting to see where the future is going to take us here. So we thank you for your attention and welcome any questions.
Thanks a lot. So any questions? Yes, please. Madsen.
Have you considered or looked at ammonia instead of hydrogen?
Yeah, absolutely.
And how do they compare?
Sean, can you maybe go back to the slide with the fuel densities? Yeah, there's hydrogen directly, as we've discussed here, and ammonia and methanol are probably the most talked about fuels for shipping right now. And the big advantages of ammonia and methanol are that it is much easier to handle than hydrogen. But you can see here it's about half of the energy density, which presents a challenge for fitting the quantities required on the vessel. But there's certainly a lot of interest in ammonia and methanol either as feedstocks for reformation to produce hydrogen on board, or to be used directly as a fuel either in fuel cells or combustion engines. So you see a lot of discussion from major shippers moving in all of these directions. I think for very large ocean-going ships, your container ships, your bulk carriers, methanol and ammonia are probably are likely fuels where they're adopting now. You see Maersk, for example, putting a lot of energy into these areas. On smaller vessels, it can be challenging, and I think that's the area where we see hydrogen directly probably is a more common fuel. Yes, and when you can refuel frequently, such as ferries and harbor craft.
Okay, I had a question. You mentioned in the San Francisco project that you were converting an existing vessel to operate on hydrogen.
Yeah.
Now, can you speak to them? Is that then a hydrogen engine, or you change the powertrain, and also how do you do the storage on that vessel?
Yeah, that vessel will that vessel will be storing fuel with compressed hydrogen and converting it with fuel cells. So one of the slides, there are marine fuel cells that are coming available on the market. This is one of them here. This is actually not the fuel cell that'll be used on that vessel, but so that vessel will actually be a hybrid. So it will be using hydrogen and diesel fuel. The other vessel that we're fueling with that station is pure hydrogen. So it's a ferry that will operate with compressed hydrogen, also 250 bar compressed hydrogen, and it will fuel about once a day.
Thank you very much for the presentation. You were referring to refilling rates as a liquid and gases. Can you name some numbers? What are the expectations for the refilling rate, as in kilograms per minute or so? Thank you.
It's a good question, and I'm hesitant to put a lot of numbers to it. The on liquid, it really can be governed by the size of the lines that you develop. So larger tanks, you can have larger bunkering lines, higher transfer rates, and in really high transfer rates, it's possible that you would use pumping instead of just pressure to drive it. On the compressed side, the real challenge is the compressors to generate enough gas for high rates and the cooling of that. Currently, the models are really around land-based applications for these fueling stations. The marine fueling is really in its infancy, and it's been only used for very small applications at the moment. So it's hard to know where it's going to go and what rates are going to be possible. But we expect that for large transfer rates, that the liquid is where we will see the marine fuels, and the smaller ferries like the in a few hundred kilograms size, there we'll probably see the compressed.
Okay. All right. Thanks a lot, Robin and Sean. So let's wrap it up. So we'll have a coffee break now, and try to be back in about 20 minutes or so. Yeah.